Hello everyone, I'm Shachee. I'm from Hicks Lab at Stony Brook University, and here I am presenting our work titled Saffire, Context-Sensitive Function Specialization Against Code Reuse Attacks. Let's start with a quick 101 on code reuse attacks. An attack scenario is considered a code reuse attack if the adversary has the ability to reuse benign code from the process's address space. Let's see how this works. This is a control flow graph of a sample application. It moves from function to function. When this application wants to interact with the operating system, it uses shared libraries, which does this on the application's behalf. Now say we had a hidden bug somewhere in the application, and the attacker is able to find it and exploit this. Once exploited, the attacker looks for gadgets in the application. Gadgets could be full function or instruction sequences. When found, these gadgets are chained to achieve arbitrary code execution. When this attacker wants to interact with the operating system, which it would in order to do anything substantial, like open a file, create a network connection, or allocate memory, the gadgets used are from the shared library. Now, one way to prevent these attacks is software debloating, where anything not needed by the application is removed. The application behaves perfectly normal, but attacker now has restricted capabilities. For example, here we have this application that uses the function foo from the shared library. Without any debloating in place, an attacker can also use another function, say bar from the library. While with debloating, the function bar is removed, as you can see. And the attacker, when tries to use it, does not succeed. Now we introduce argument level specialization. It's understandable that not all functions can be removed by function debloating. Case in point, the function foo from the previous example. We can further extend the impact of debloating by restricting arguments passed to these critical functions. Here, the application has two instances of function foo being called. Even with function debloating, an attacker's call to the same function foo would be successful. Argument specialization, though, function foo is specialized. It's specialized to only accept arguments from the original code base. In this case, the integers 1 and 2. When an attacker calls foo with some other argument, it fails. Now the question arises, is the problem solved now? Do we need further work? To understand this, let's think about it. Applications invoke multiple library calls from different points in the source. Each of these calls have their own set of arguments. The effectiveness of argument level specialization lies in our ability to find these arguments. And as expected, not all possible values can be known in advance. Here is a simple example of library call open in server application Nginx. We have two different calls. In the first case, the file to be opened is found statically, that is /dev/port, but not in the second. Thus, an application-wide policy would put no restriction on the name argument because there's this one instance where we don't know what would be opened. Thus, an attacker, if is able to exploit a bug in Nginx, can reuse these call sites and open any arbitrary files. With context-sensitive policy, though, each of these call sites would be individually specialized. Thus, the attacker would not be able to open any arbitrary file using the first instance. This brings us to our tool, Saffire, which in a nutshell creates a custom function for each call site that is tailored only to the arguments for it. The application source with two instances of function foo would go through our tool and its two phases, static and dynamic binding, which we will learn about next, and Saffire transforms the call instructions to call specialized functions. The first step in the process is static argument binding, where we fix argument values that can be statically identified at the source code level. For instance, say this is a snippet of code. We have an open file name, open library call, which takes in one of the two file names depending on some condition. So the file name could be file1.txt or file2.txt. In the first step of this process, we first identify the call site. Then for each of its argument, we explore the paths where it could have been initialized. In this case, we have two different paths, depending on whether the condition was true or false. And then we look for all the possible values that could be assigned to it. which are file1 and file2.txt. The call site is then updated to call a new specialized function, custom open in this case, and this new function enforces the static values at runtime. Let's see how many arguments could be statically known for various library functions across 11 tested applications. The x-axis are library functions grouped by the application, while the y-axis provides percentages of arguments that can be known or fixed. Without going into much detail, we can see that about 50% of the arguments could be statically known. We still have about 50% that we could not get values for. For this, we have dynamic argument binding, which is phase 2 of our tool. Dynamic argument binding is a narrow scope form of data integrity to bind such arguments. Some arguments can only be known at runtime, like file descriptors, memory addresses, and user inputs. To identify such arguments, in this case, we have a call to the function write, one of the arguments to which is the file descriptor created by another function called somewhere before in the code. Now we find the origin and generate its hash, the hash of the file descriptor, and store it in a secret shadow location. Call site, as was the case with static argument binding, is updated to call a specialized function. This specialized function, custom write, when executed, reads the hash from the same secret shadow location and verifies the argument. Now to see what we gained from this phase. These are the percentages of known arguments with only static binding. It's the same plot that we previously saw. Adding dynamic binding to it, we can see that it provides us a near complete coverage on the arguments passed. Now moving on to security evaluation for our tool. For ROP, or return-oriented programming attack payloads. ROP attacks are a popular code reuse attack techniques. We tested Saffire with 11 popular applications and used them against a set of 17 proof-of-concept exploits, 13 of which aimed towards arbitrary code execution, while 4 aimed to update memory protections. Of the 11 applications that we tested, Saffire is able to block all 17 payloads in 9 of them, while in case of 2 applications, Saffire was able to block 12. Detailed explanation of our experiments and results can be found in the paper. We also tested Saffire against a few real-world exploits, one of which is control Jujutsu in Nginx. Nginx source contains this code, which executes a binary passed to this function using the library called execv. An attacker can directly call this function with their choice of argument and would be able to achieve arbitrary code execution. With Saffire, however, we were able to deduce that this function can only be used to call the Nginx binary itself and no other executable. Thus, we created the secure version of the application Nginx, where malicious code execution would be tested against this argument, and anything other than the Nginx binary itself would be blocked. In conclusion, we presented Saffire, a context-sensitive specialization, function specialization tool, which works in 2 phases. In phase 1, static argument binding, we eliminate arguments with static values and concretize them in the specialized function body. Step 2 is dynamic binding, where we provide a narrow scope data integrity to restrict acceptable values for arguments that cannot be statically derived. We tested and confirmed that real-world code reuse exploit against applications like Nginx, Chrome, and Firefox could be successfully broken. Thank you, and we'll be happy to take any questions.